Hello and welcome to my off-brand TED Talk about the first quarter in chemistry. First off, we're going to go over some laboratory safety, which is something that's very, very important in a setting like this, as a lot of the chemicals that we'll be working with can be very dangerous at times. In some of the accidents that can be caused can usually be prevented by using the use of proper behavior. Some of this behavior before the lab is make sure that you're wearing proper attire, so closed-toed shoes, safety goggles, lab coats, tie up any hair. Basically try to not get anything on you or have anything on you get in the lab. This does include food or drink. Make sure to finish any of that before you even go to the lab station, as oftentimes people will mistake stuff that's in the lab for their food or drink, or it'll get on their food or drink and then they'll eat it, and that's not a good time. Trust me. Make sure you also have all the right equipment, and all that equipment is functional and working properly. You don't have any chipped beakers. Your sparking stick is actually sparking, and you're not just going to be leaking gas from your Bunsen burner into the air. All that good stuff. During the lab, some precautions to take. Again, don't attempt to eat anything, including your own food or drink. Try not to introduce foreign substances, so anything that might not be part of the lab, into the lab, or do anything that the instructions don't tell you to do, because they can result in unwanted consequences. Anytime there are liquids, including water, being used in the lab, or something that is being heated in the lab, make sure to wear safety goggles. You don't want something in your eye. It's really not a good time. Never point the open end of a test tube or anything that's bubbling in a beaker toward anyone, especially if it's being heated, as this really can hurt your face if you get some hot chemical on your face, or even worse, in your eye. This goes for you too. If you need to smell something, do not put the beaker directly under your face. Hold it a couple feet away from you and waft your hand right over it and towards your face to get the smell if you need to smell something. As well as do not leave any active substance, so any bubbling substance, any boiling substance, or any equipment like a hot plate or burner unattended for any reason during the lab, as they can easily get out of control, and they all require some special monitoring. Once you're done with the lab, make sure you dispose of all the substances properly. Usually not down the drain. Sometimes you will, but make sure to ask your instructor first, as they're going to know what you cannot put away where. You'll usually see before every lab, they will instruct you to what to do with the chemicals after you're done. Make sure all your equipment is put away, and anything that needs cleaning is put in a place where it will be cleaned, or you have cleaned it. And then also, until everything in the lab is put away, including all the equipment, do not take off your safety glasses or your lab coat until everything's done. And always wash your hands after the lab, and especially if you're planning to go eat right after. If something does happen during the lab, something small like a chemical spills onto the counter, or you chip a beaker, don't panic. Call your instructor over. They'll know how to handle with the problem. But if an emergency occurs, such as you catch yourself on fire, or something gets into your eye, go directly to the proper tool in the classroom. So eyewash station, safety shower, fire extinguisher, fire blanket, all that good stuff is important to know where that is, and to know when to use it if an emergency does occur. Next up, we're going to move on to atoms. Now, atoms, as I'm sure you guys know by now, are tiny particles that make up everything, and each version is its own different little element with its own properties and place in the periodic table. And they're made up of these three parts. First off, we're going to start off with the proton. Now, they're the positively charged atoms, and they're in the very middle in a place called the nucleus. And they're what ultimately determine what element that atom is. For example, any atom with 8 protons is going to be oxygen. That's never going to change. Any element that ever had 8 protons or ever will have 8 protons is and will be oxygen. It's also, for this reason, it's also known as the atomic number, because it will always represent what element or what type of atom it is. And it's mainly way for chemists to organize these atoms. And so atom number 1, hydrogen, will always be atom number 1 hydrogen, and you will always refer to it as atom number 1. And atom number 118 oxygen, I think it is, something like that, and that's always going to be atom 118, and that's just an easy way to identify them. So, and it's why it's always at the very, very top of a symbol that you will see on the periodic table. You'll see that atomic number up there. Next up, we're going to talk about this atomic mass, which is mainly affected by these guys, the neutrons. They're neutrally charged, they really don't have any charge at all, and they're packed into the nucleus along with the protons. And they're basically there to prevent the atom from breaking itself apart, because you have all those positively charged protons. They're all repelling each other, and they need the neutrons to kind of just help them stick together. And yeah, they mainly affect the atomic mass, as they weigh, or they have a very similar mass to protons. And the more you have, obviously, the more mass you're going to have. These next ones, though, really don't weigh anything. These are the electrons. They're much, much smaller, and they have negatively charged, and they're negatively charged, and they orbit the nucleus in the electron cloud, and they're organized into levels called shells. And each shell can only hold a certain amount of electrons before a new shell needs to be added. And that shell is what ultimately determines where it is and what atoms it's in the same rows and columns with on the periodic table. The rows are determined by what outer shell, what's the outermost shell in that atom that has electrons on it. For example, the two atoms in row 1 have their average shell as the first shell. All the elements in row 2 have their outermost shell as the second shell. It goes on like that. And then the columns is determined by how full those shells are. All the atoms in column 1 have 1 electron in their atom shell. All the atoms in column 2 have 2 electrons in their outer shell, at least in a neutral charge. And those electrons in that outer shell is what's affecting these things, the bonds. And most substances aren't really made up of just one atom. Most are made up of many atoms that are bonded together to make molecules. And in order to make them, they obviously need to be bonded in some way with their electrons. Now, there are 2 main types. This first one is ionic. It's always going to occur between a metal, so basically an atom on the left side of the periodic table, and a non-metal, which is always on the right. Those aren't like the scientific terms. There's obviously a big split in the middle, but basically ionic bonding happens when this metal basically gives away one of its electrons to the non-metal. For example, we have lithium here, atom number 3. Atomic number 3, so it's got 3 protons and 3 electrons to balance out that, so it has a neutral charge, but it only has 1 electron in this outer shell. But fluorine, on the other hand, has almost a full outer shell. This second shell can hold 8 electrons, and it has 1, 2, 3, 4, 5, 6, 7. And so basically it just takes that 1 electron from the lithium, which now leaves the lithium with 3 protons and 2 electrons, meaning that has a slightly positive charge, and it leaves the fluorine here with with 1 more negative charge than positive, making it slightly negatively charged. And that negative to positive charge difference basically attracts the 2 atoms to each other, and they bond that way. And then compared to covalent bonding, covalent bonds will always occur between 2 nonmetals, or a nonmetal and a metalloid, and they involve those 2 atoms sharing electrons. So let's say we have 2 of these hydrogens. These hydrogens have 1 electron just floating around there in the electron cloud, which is this little black piece here. And then when 2 of them come close to each other and they both want 2 electrons, or they both want 2 electrons because that's how much is needed to fill up their first shell, they will bond together in a covalent bond, meaning that the 1 electron that this guy had and the 1 electron that this guy had are now in a kind of oval shaped orbit rather than the circular ones around each atom, and basically they're just being shared between those 2 atoms. And next up we're going to move on to reactions. Now there are 5 types of chemical reactions that you're going to see. Synthesis, decomposition, combustion, single replacement, and double replacement. And every single one of these reactions that you will ever see will follow the law of conservation of matter, which is basically you can't have more or less than what you started with. You always have to have the exact same amount. And we're always going to have the exact same amount of atoms of each type of atom on both sides of the reaction. So this arrow right here represents the reaction happening. And so we see we have 2 Ca atoms and 1 O2 molecule, which is 2 of these O atoms. And then the reaction happens, and we've still got 2 of these Ca atoms and 2 of these O atoms. So we can see that there's the same number of everything here. And every single equation you're going to see is going to have that. And that's the law of conservation of matter. Now, onto the actual reactions themselves. Synthesis is what we see here in this reaction, and it's basically when 2 atoms or an atom and a molecule or 2 molecules combine together to make one big molecule. And for example, we can see right here those CAs and the O2 molecules bond together to make CaO molecules. And decomposition is the exact opposite, starting with a big compound and then breaking it up into its smaller pieces. Replacement reactions, on the other hand, are basically what the name suggests. So basically, you're going to have a compound and a spare element, or 2 compounds, and they're basically going to switch out one of the elements in the compound for an element in another compound or another element. In single replacement, it's that one element, so you'd have a compound and one element, and one of the elements in the compound would get switched out would get replaced by the spare element. And in a double replacement reaction, which we have here, we can see that one part of each element, or one part of each molecule is getting switched out for the other. So we see when we start off, we have the K element, the K atoms mixed with the I atoms, and the Pb atoms mixed with the NO3. And then the reaction happens, and now the Pb is with the I, and the Ks are with the NO3. And that would be a double replacement reaction, because we're doing double the replacement that we would in the single replacement. And the final type is combustion, which is special from the rest because combustion reactions will always have the exact same amount, or the exact same products and reactants. They're always going to start out with these hydrocarbons, so hydrogens and carbons in various states, and that's the only really thing that can differ between the reactions, and oxygen, and they're always going to end up with carbon dioxide, which is the CO2, and water, which is this H2O. And that's how you would spot these. And as the name suggests, it's combustion. It's usually blowing stuff up or lighting them on fire. It's another pretty easy way to spot them. But yeah, that's about it. Thanks for watching.